All right, I think we're just going to wait just a few moments for our folks to kind of drop on in, give everyone a chance to make notice that we are alive. Let me make sure I have all my ducks in the row. All right, we're doing good. Okay, I think everything is in order. So let's get this show on the road. Greetings, tech artist fans from around the world. Ooh, I might need a microphone on this. As I was saying, hey, it is Friday. It is 12:30, and the mass chaos and mayhem have already started. So this must be Tech Art Talk Live. Yeehaw! Yes, sirree, gang. All right. The last few weeks we've been working on HLSL, and for the last just a couple weeks we've been focusing just on post-processing alone and how HLSL can be used to manipulate your post-process shaders and so forth, and it's really super powerful. And the last couple weeks I didn't get an opportunity to go over this really awesome convolution technique called edge detection. Now that's what we're going to focus on today. So today's lecture is going to be just a little bit itsy bitsy because we're just going to be focusing on one texture, but mind you, this is a good compact technique, so strap on your jock strap, everyone, and we're going to get ready to rock and roll because we're going to go dealing with edge detection. Yeehaw! All right, so let's go ahead and get onto this. Ooh, wrong image here. Ooh, that's not even good here. Let me get this going here. All right, where's my PowerPoint? PowerPoint. Where is it? Make it show, please. I think that's showing. So let me go ahead and switch over to it. All right. So let's get on to the lecture. Yes, we're dealing with edge detection here, folks. All right. All right. So edge detection is used for a whole bunch of things, and it's done by identifying contrasts between neighboring pixels. When two pixels, like one is bright and one is dark, then that creates a contrast in between them. And that's what this convolution filter does, is it examines adjacent pixels and it looks for bright contrast with each other. And where it finds a bright contrast and goes, there's a bright contrast here. There must be a line here. And so a popular algorithm to exploit this is something called a Sobel operator. And a Sobel operator does this in a really fancy, convenient convolution sort of way. And it's a simple two-pass filter that does things in horizontally and it does things vertically, kind of like the way we did things with the Gaussian blur, but it's a simple two-pass convolution filter that's pretty easy to implement. It's a little bit difficult to understand at first, but it's got a super easy implementation, so hang on tight. We're going to try to explain exactly what it's doing underneath the hood. Okay. Now, if we're going to be dealing with the Sobel pass, let's just suppose we're dealing with it, dealing it from left to right. We're going to deal with this convolution filter. And this convolution filter is just a 3x3 filter. And notice that it's got values on the left side. That's 1, 2, 1. Nothing in the middle. And then on the right-hand side, it's got -1, -2, -1. And so what these are going to do is identify and kind of like exasperate the contrast being between this. And so what we're going to do is we are going to multiply our convolution filter against our center pixel, which is in this diagram pixel number 4, and it's kind of like it's 8 neighboring pixels. It's going to multiply the matrix of our convolution matrix and our pixel matrix against each other. And because we got a bunch of ones and a bunch of zeros, this kind of makes the whole thing actually pretty simple. And then we got this convolution formula. And so we're going to do, okay, we're going to go convolution x versus pixel 1, 1, which is the center pixel, or pixel number 4 in this situation. It's pixel number 0 minus pixel number 2, plus 2 times pixel 3 minus 2 times pixel 5, plus pixel number 6 minus pixel number 8. And that will give us all of the contrasting pixels going from left to right. Okay, easy enough. Well then, you kind of, put all the puzzle pieces together, and you should know what's going on if we're going to deal with this vertical, kind of like going up to bound. Okay, so we're going to start off with the bottom having the positive values, so with 1, 2, 1, and then the top row is going to be -1, -2, and of course -1. And then we're going to do the exact same thing. We're going to get our pixel matrix that we have with our hero pixel here at pixel 4 right at the center. And that's going to be right at the center of our 3x3 neighbors and so forth. And we're going to multiply that against our convolution matrix. And this is the convolution matrix we get. And it looks real similar to the Sobel operator we created for the horizontal pass. And that's pixel number 6 minus pixel number 0 plus 2 times pixel 7 minus 2 times pixel 1. And then we're going to add that with pixel 1 minus pixel 8 minus pixel 2. All right, and that's going to end up with our 2 convolution values, one horizontally and one vertically. Okay, you're saying probably that's cool. You've got these 2 convolution values that kind of like produce into 2 floating point values, but what do you go ahead and do with that? Well, what we're going to do is we're going to add them together. And then when we add them together, we're going to compare them against some kind of threshold. And what that threshold is, it kind of depends. It kind of floats around, and that threshold kind of defines out what our center point or what our minimal edge detection is going to be. So if the sum of our convolutions are greater than the threshold, then we're going to return white. If the sum of our convolutions is less than the threshold, then we're going to return black. And that's really the algorithm. It really is that simple, folks. We're just going to... But mind you, at the beginning of all of these convolutions, we do have to get our center pixel, and we aren't taking the actual color values. We are actually taking the intensity or the luminosity of our text, and that means we are going to be doing that dot product with all of these pixel values against that little vector that transforms our pixel into a luminous value, or basically a grayscale value. And so that is how we're going to make this actually be happen. So I'm going to bop on over to here, and I'm going to change things up a bit, and I'm going to move things over into my demo. All right, there is our demo screen, and I am just going to pull up my notes here real quick. All right, so what we're going to do is we are just going to create a post-process material, just as we would normally. And I'm going to drop in here. Come on, give it to me. Hello. There we go. All right, so let's create a new, and my machine has just suddenly decided to go into slow motion mode, and it's not going to cooperate. All right, so I'm going to create a new folder, and I'm going to call this TATL for Ticker Talk Live, obviously. I'm going to drop inside TATL. And my machine is just creepy crawly going at a slow pace now, and it's like, oh, okay, oh, please, you're going to have to be patient with my latency. Thank you very much. But we're going to go ahead and create a brand new material. And I'm going to call this PP underscore edge detection. Edge detection. Okay, we've got our edge detection, so I'm going to drop into our PP edge detection, and I'm going to move this up here. Feels like I'm driving in sludge here, but because we're going to create a post process here, we're going to turn the material domain into a post process, and our shading model, we're going to make it unlit. Yeehaw. So only thing we're dealing with here is the emissive color in our material. All right, now we're going to need a couple of nodes to support this, and the first node that we support this with is our scene texture. And our scene texture is actually our render buffer, or our render target. And so the scene is actually being rendered at 60-some frames per second, and it's pretty fast, and it's coming through here. And instead of going to the frame buffer, it's coming through the scene texture here. And as we can see, if we plug that right into here to the emissive, it just passes right on through. And so what we see here is just the simple the scene rendered as is. But in order to support this, we're going to need a couple of scalar parameters. So the first scalar parameter that we're going to need is the Sobel threshold. And now this is the minimum amount of value that we need in order for the Sobel operator to pick up. It basically means we're going to use this number to help dial in and what produces the best amount of edges in our line. And for default, I'm just going to put that at 0.1. Nope, that didn't work. So let's try to do this again. 0.1. Very good. All right, let's create another scalar parameter. And I'm going to call this scene dilation. Okay, scene dilation is kind of a little bit of a foobar situation that I put in here in order to help refine and fine-tune our technique just a little bit. It still works pretty good. So this is like a little bit of a kludge factor because I kind of like I don't like the way just working with 1 pixel per pixel, sometimes a little bit more than 1 pixel and so forth. And this scene dilation is going to help refine that a little bit. Okay, so what we're going to do next is we are going to create a custom node. Okay, I've got my new custom node, and I'm going to call this my Sobel operator. All right, we've got my Sobel operator, and this is going to return a float 4 because we're going to deal with the full color, and we're going to agree 3 inputs. And the first of these is the scene texture, and that's going to come in right from our render target. And the next of these is going to be our, let's see, that's going to be our Sobel threshold. No, I don't want Sobel threshold none. I just want Sobel threshold. Yep. And then the last one is going to be our scene dilation. Scene dilation. Okay, cool. So let's get to the whole process of right. We're going to hook up our color into the scene texture. And then we are going to hook up our Sobel threshold and our scene dilation right into there. And then we're going to hook this up to our emissive color. And we should get a white screen. Why? Because right now we're returning just 1 right into there. But before we get going on to create the code into our custom shader here, our Sobel operator, I wanted to just create this code inside of Sublime here in order to be a little bit more visually helpful. So I'm going to go ahead and get rid of all of this crap here. And let's take a look at what we got here. All right, first what we're going to do is we're going to declare a matrix. It's going to be a 3x3, so it's got 9 slots long. And this is going to be our incoming texture value. And so it's a float. Notice that it's just a float, meaning that we're not dealing with the full colors. And that's because what we're going to do is we're going to translate each one of our colors into a grayscale value. And we're only going to take the red channel for that since we only need one thing. So it makes it a little bit smaller. All right, and we have an index that's going to help us identify things. And then because we're working with the UE4 post processor, our scene texture ID is going to be number 14. Our texel size is going to come in as our view times the view size, inverse size in the ZW factor. And we're going to create a little vector here. It was our luminosity vector, and this is going to be our little vector that we're used in order to create our grayscale values. All right, I've got I'm going to get the UV coordinates by calling get default scene texture UV, and I'm going to send it my parameters and my scene texture ID. And then I'm going to construct the image matrix, and that's going to be made up of the floating point pixel values of this. And so what I'm going to do is I'm going to create a 2x2, well, actually a 2-dimensional for loop. And instead of going from 0 to some kind of number, I'm going from -1 to 1, honestly. I'm going to do that horizontally, and I'm going to do that vertically. And then so I'm going to compute the first step as an offset, which is just my my I and my j size, and then I'm going to multiply that by my texel size, because the texel sizes may not be one-to-one according to pixel size. They might be a little bit bigger, they might be a smaller, and so that's why we're multiplying it by the texel size. And just for safekeeping, I'm going to throw in a multiplication to the scene dilation, which is really just kind of a fudge factor that might edge things up a little bit larger or a little bit smaller in order to get the exact kind of resolution that we're looking for. Then we're going to take our sample, which is going to do our scene sample. And then what we're going to do is take that sample, we're going to do the dot product versus our luminosity vector, and that value is going to get put into our index value into our matrix. And so that's going to create our 3x3 image matrix. All right. And so next comes the fun part, where we're actually going to do the convolutions. Now we went through and we calculated what these convolutions were ahead of time before we got into creating it in UE4, and they're really pretty simple. So we're going to go for the sum x equals t6 minus t8 plus 2 times t5 minus 2 times t7 plus t0 minus t2, and that's going to be horizontally. But vertically, what we're going to deal with is sum the t6 minus t0, 2 times t7 minus 2 times t1, t8 minus t2. All right, so here it is. Those are our two horizontal and our vertical, and these are going to produce our summation or our convolution values. And here comes the magic, folks. All right, then what we're going to do is we're going to create a new float 4 destination. So if our sum is greater than our Sobel threshold, then we're just going to return white. However, if our sum is less than the Sobel threshold, then we're just going to return black. And I'm going to make this greater than or equal, just to add just a wee bit more, just in case. So we've got our Sobel times the threshold, and then if it's less than the Sobel threshold, then we're going to return black. And it's really that simple, folks. So what I'm going to do is copy all of this stuff. Hello. Get that in there. Go into my custom operator and just drop that right in here. All right, there we go. All right, there we can see it's actually starting to behave. It looks a little bit funky just because it's not really dialed in yet. And that's what we're going to do, is we're going to dial in these values. So I'm going to press save in order to kind of like get things going. So let's go into our scene and let's create a material instance out of this guy in order to get it so that we can dial this in. So I'm going to call this mi underscore edge detection. All right, and so here's our mi edge detection. And so what I'm going to do is look for my post process filter. Okay, there's my post process volume, just what I needed. And then I'm going to come down to, where is it? I always lose this. Global illumination, illumination, and my machine is like really slow. Depth of field, color grading, film, color illumination, reflections, mobile depth of field. No, where is it? Depth of field. Oh, I can't believe I can't remember where this is. Reflections. Aha, post-process materials. There it is, hanging out way down low. I had to find it. Okay, I'm going to add this. Come on. There you go. And then I'm going to choose an asset reference. And then for this, I'm going to make sure that it is my MI edge detection. There we go. And so it looks blacked out, but that's because we haven't dialed it in, folks. But let's go ahead and dial this in. So I'm going to go in and isolate my MI edge detection. Bring this off to the side here. Okay, so let's bring in these values. Okay, so we've got the Sobel threshold. Let's go ahead and bring this up. Whoa, it got bright really quickly here. Okay, so let's bring in our scene dilation. Ah, there we go, gang. We've got this. It's going a little bit slow here, but let's go ahead and modify this Sobel threshold just down a wee bit. No, my machine is just so slow. Okay, let's bring it up just to kind of refine it just a bit, and then our scene dilation is going to fine-tune this just a wee bit more. Okay, yeah, and we're going to get the, oh, we reached our threshold, and so I think this is right around, yeah, 0.5. I think is right where we have to go. All right, now if we wanted to, we can make this a little bit more precise, but we're actually getting some pretty good values here. All right, so if we kind of like scoot around here and go around, oh my gosh, my machine is really lagging here. We can kind of identify and where all the corners. Now this can be shown in the very fine filigree work inside of the doors and the windows, and that really comes across and shows, and we can see the lines inside of the tiles on the floor of our settings. Okay, I'm going to go ahead and save this, and then I'm going to get out of here, and then we're going to move on to our final goodbyes here. Okay, I'm going to get on to here, and then I'm going to make sure that my PowerPoint is moved forward here. Okay, and we're almost there. Almost there, folks. Thank you very much. All right, great. There we go. Okay, folks, that's going to wrap it up as far as our visual effects, and especially with dealing with post-process filters are going to concern. Join us again next week. And can you believe this is the 29th? Man, that's like Halloween. That's like our last day before like the slide to the end of the year, and then it's just going to get really very fast. But next week we're going to start working on using HLSL in order to calculate our shadow mapping. And the shadow mapping, it's going to take a few lectures to get through, and we're going to start working on just on shadow projections next week. So that's what we have in store for next week. All right, now if you liked what you saw today, go ahead and press the little subscribe button down in the lower corner and subscribe to us. And if you want, check me out. I'm Chris Rhoda. You can check me out on Facebook and on LinkedIn. Or otherwise, you could check out TechArt.edu, which is the kind of banner under everything that we're doing here with TechArt Talk Live. And check us out on Facebook and on LinkedIn. Okay, otherwise, you could check us out on TechArt.edu. Go to the website. You can opt in. And if you opt in, go to TechArt.edu.com. Give us your name, give us your email address, and we'll send you information if we were to ever actually create any information. Well, it's good to collect it all the same. Anyway, that's what we have in store for next week. We're going to be going into shadow mapping, which itself is really, really fascinating. Thank you very much for joining me today, and I'll see you all again next week for, the Halloween show? Oh my gosh, that means I'm going to have to create a costume? Oh my golly. Oh well, every day is Halloween, right? Yeah, okay. Well, thank you very much for joining us. I'll see you again next week. Arrivederci.